All right, so we are back for the final fourth part, which I am calling the fourth isomorphism theorem. Um, I believe others call this the correspondence theorem for submodules or something, and yet others call it the lattice isomorphism theorem, which I'll explain why maybe later. And I think there might be other things that people call the fourth isomorphism theorem. This is the one where the naming is the least consistent among people, but I'm calling it the fourth isomorphism theorem, so you can deal with it. And it tells you what the submodules of a quotient module look like. So if I have a submodule of M, then the submodules of M that contain N are in correspondence with the submodules of the quotient module M mod N. And it's actually an isomorphism of lattices. That's why it's called a lattice isomorphism theorem. When you have a algebraic structure, all of its substructures typically form another algebraic structure called a lattice. And I don't even particularly remember what the definition of a lattice is, but I think you need to show something about the intersections and the sums of submodules if you want to show that this is actually an isomorphism of lattices. I am not going to do that. I'm just going to show that it's an inclusion preserving bijection, and you can look up on Wikipedia the whole thing with lattices. But anyway, okay, let's get into it. So I want to show there's a bijection. So I'm going to name these two sets of things. So let's call fancy A the set of all the submodules of M that contain N. So A is going to be all of the S submodules of M such that S contains N. And then I'm going to call fancy B the set of all the submodules of M mod N. So it's going to be the T submodules of M mod N. And these are just the script A and script B are just sets, right? So I'm not going to imbue them with any other algebraic structure. They're just sets for now. And I need to show the thing that I need to show in this theorem is that A is in bijective correspondence with B. So I need to show a bijection. I want to show a bijection phi from fancy A to fancy B. Okay, so what is this bijection going to be? So I'm going to define a map phi. Again, it's going to go from fancy A to fancy B, and it needs to just be a function on sets. So I'm going to take from A a submodule S of M that contains N, and I'm going to map S by a phi to S divided by N. So basically, I'm sort of applying the quotient map, or I'm taking the image of the quotient map. So right, this is the set of M. This is the set of cosets S plus N, where S runs through S. That's what this quotient module is. Okay, so that's the image. That's what I'm going to call. That's the set I'm going to call phi of S. So, first I should show that this is actually an element of B. And to show that it's an element of B, I just need to see that it's a submodule of M over N. So first, phi of S is a submodule of M over N. But phi of s is s over n, right? So I claim it's somewhat obvious that this is a submodule because, right, because s is a submodule, and if I have s of s plus n plus, let's say, s prime plus n, this is just equal to s plus s prime plus n, and s plus s prime is in s because s is a submodule. Use a different colored pen, right? This thing is in S. And so the coset is in S over N. And 0 is in it. 0 plus N is in S over N because 0 is in S. And then also if I take R times S plus N, this is just RS plus N, and RS is in S because S is a submodule. So this is in S over N as well. Okay, so it's a submodule. Awesome. How do I show that it's a bijection? Well, in order to show that something is a bijection, one of the ways is show that it's onto and one-to-one. But sometimes the better way is to construct an inverse for it. So I'm going to construct an inverse. So to show that phi is a bijection, I haven't done this before, so I'm going to explain it in excruciating detail. We can show there exists another map theta from script B to script A such that theta composed with phi is equal to the identity on A, and that phi composed with theta is the identity on B. Right? The identity map is just the map that takes a thing to itself. In other words, I can show that there exists a phi inverse from fancy B to fancy A. So I'm gonna construct an inverse, but before I construct the inverse, I need to explain or recall. So recall, remember from the quotient modules video, I have a quotient map. Anytime I have a quotient module, I get a canonical quotient map. And I called it Q, that goes from M to M mod N. And Q was actually a R module homomorphism. And it's surjective. So it's a surjective R module homomorphism. The quotient map is. So I'm gonna define the inverse using this because it sort of stands to reason, right? The forward map from A to B is basically taking the image of the quotient map. That's in fact, that's exactly what it's doing. Phi of S is just the image of the quotient map. Right, phi of S is the same as Q of S. It's the image of the quotient map. So it stands to reason, perhaps if we take the pre-image of the quotient map, possibly that will work. Okay, so define theta from fancy B to fancy A by, so if I take a submodule T of M over N, I'm going to map it to Q, what looks like Q inverse of T, but what I mean is pre-image. Have I defined pre-image? I don't think I've defined pre-image. So the pre-image, okay, aside, the pre-image, which the notation is the same as Q inverse, but Q is a surjective map. It doesn't have an inverse. Okay, so Q, the pre-image of something is in the pre-image of a map, if and only if that thing maps into that set. So the pre-image of a set is all of the things that map into that set under the map. So that's what it means. X is in the pre-image of T under Q, if and only if Q of X is in T. That's what it means for something to be in the pre-image. I don't know if I've used that definition before, but it's not the inverse. It's the pre-image. If I have a function, maybe I should draw a picture of the pre-image. So let's say that I have a function and all of these elements map into this set. Then if this is like the set T, then this is the pre-image. It's all the elements that map into there. Where that's the map Q. Okay. Sorry, I should stop babbling so much. And also remember that T is a submodule of M mod N. So it's a set of cosets of N. But this map, what do I need to check first? I need to check that this map even makes sense. It should go from B to A. So if I take some submodule of M mod N, I need to get in the image of this map a submodule of M that contains N. So I need to show that in fact the pre-image of T is actually a submodule of M, which contains N. And I should write in like set notation what the pre-image is, right? The pre-image is the set of all of the elements of M such that Q of M is in T, which means, right, since Q is the quotient map, this is all of the little m in big M, such that little m plus n is in T. That's the quotient map takes an element and sends it to its coset with respect to n. Okay, so I need to show that this is actually a submodule that contains n. Showing that it contains n isn't terribly hard. So n is contained in the pre-image of T, since if I pick any n in n, n plus n, this coset is equal to 0 plus n. And 0 plus n is certainly in T, because T is a submodule. Right, submodules always contain 0. So we know that the pre-image contains n. Then we need to show it's a submodule. So to show it's a submodule, the first thing I'll do is show it contains 0. So 0 is in the pre-image. Again, since 0, Q of 0 equals 0 plus n, which is in T. And then I need to show that it's closed under addition. So suppose that suppose that x and y are both in the preimage of T under Q. Then by definition of what that means that Q of x is in T and Q of y is in T. And then T is a submodule, so I can add two elements of a submodule and get something else in the submodule. So Q of x plus Q of y is in T. And then because the quotient map is an R-module homomorphism, that means that I can write this as Q of x plus y. I think I made a big deal at some point about the quotient map being an actual structure preserving map, and that's why we need it. So that means Q of x plus y is in T, but then that means that x plus y is in the preimage of T. And there we go. So we showed that that this is closed under addition. If I have some ring element and I take an element of the preimage, whoops, then I need to show that that this is actually closed under scalar multiplication. So Rx. Okay, sorry. So Q of x is in T, but T is a submodule. So T is closed under scalar multiplication by R. So R times Q of x is also in T. That's because since T is a submodule, and then because Q is an R module homomorphism, that means I can put this R inside here. So Q of Rx is in T. And then Rx is in the preimage of T under Q. And then we're done. So okay, so I don't know if that was confusing or not, and nobody's here to tell me, so I'm gonna just go over it again. We define this map. I take a submodule of M mod n, I map it to its preimage under the quotient map. I just showed that, in fact, this is actually an element of A, and I showed that it's actually an element of A, right? A was the set of all submodules of M that contain N. So I showed that Q inverse of T contains N, right here. And then I showed that Q inverse of T is actually a submodule of M. And okay, and then now we have these two maps, one that goes from A to B and one that goes from B to A. And I need to show these two things. I need to show that they're inverse bijections. So to that end, let's just compute some stuff. So I need to compute theta composed with phi. And phi starts in A. So I need to apply this to an element of A, meaning S, a submodule of M that contains N. Okay, and then theta of phi of S is theta of S over N, right? And the map theta is the pre-image of S over N, which means the set of elements of M such that M plus N is in S over N. Right, that's what the preimage under the quotient map means. But then this is right, if for this coset to be in S over N, I need little m to be in S. So this is the M in M, such that M is in S. And then, since S is already a submodule of M, this is just S. So theta composed with phi is equal to the identity on A, right? It takes S and it spits out S, spits out whatever it takes in. I need one more slide. All right, I really have to sneeze. Okay, now I need to compute the other one. I need to do phi composed with theta, and I need to feed this a submodule of M mod N. So I'll call it T. Okay, so theta of T is this pre-image that looks like Q inverse of T, but it's not an inverse. So it's theta of the set of all the M in M, such that little m plus n is in T. And then when I apply phi to this, right, phi is just applying the quotient map. So I'm taking all these elements little m and sending them to their cosets under n. So now I just have the cosets m plus n in the quotient module m over n, such that m plus n is in T. That's what doing phi does. It sends things to their cosets. So then this is just the cosets m plus n, where m plus n is in T. But that's nothing but just T. T is a set of cosets anyway. So this one is the identity as well. So, but it's now the identity on B, submodules of M mod N. So phi composed with theta is the identity on B. Okay, so therefore, theta and phi are inverse bijections. So we've proven the theorem. And then I'll remark just one last thing. This bijection preserves inclusions, right? If I have that A is contained within S, then the submodule A mod N is contained in the submodule S mod N. And this is more or less obvious, right? This is the set of cosets of A plus N, where little a is in A, and this is the set of cosets S plus N, where little s is in S. And if A is contained in S, then there's more things in the right-hand side one. So it's an inclusion preserving bijection. In fact, it is a lattice isomorphism, but we're not going to talk about it. Okay, so I guess that's all I have to say about algebra for a while. Thanks for tuning in. Bye.